This is part 3 in my series on the preliminary mathematics of cryptology. I am first going to go over what it means that two numbers are coprime, and then I'm going to go over the multiplicative inverse and why that's important for cryptology. So let's get started. In my previous video, I showed you how to use Euclid's algorithm to calculate the greatest common divisor of two numbers a and b. In some cases, the greatest value that divides two numbers a and b is going to be equal to 1. And when that's the case, we say that a and b are coprime. So I'm going to write that up here. If the GCD of a and b, we just finished at a, is equal to 1, then a and b are coprime. This coprimality property is really important for cryptology, and I'm going to show you why. First, I'd like to remind you that we, in the first video, defined the set of integers Cm to be the set of values from 0 to m minus 1. In this example here, we're going to use a equal to 4 and m equal to 9. Which means that the set of integers that we're operating with is C9, which is the numbers 1, 2, 3, 4, 5, 6, 7, and 8. I'll just quickly go through the calculation to show you that 4 and 9 are coprime. So first we'll have R0 equal to 9, R1 is equal to 4, 9 is equal to 4 multiplied by 2 plus 1. We'll take 1 down. 4 is equal to 1 multiplied by 4 plus 0. Remainder 3 is equal to 0. And so the greatest common divisor of 9 and 4 is equal to 1, meaning that 9 and 4 are coprime. I'm going to put a theorem up on the screen, and I'm going to read it aloud as well. The theorem states, the congruence A multiplied by x congruent to B modulo m has one unique solution x in the set Cm for every value of B in the set Cm, if and only if the greatest common divisor of a and m is equal to 1. That's a lot of information, and I'm going to go through an example here to show you exactly what that means with real numbers. I'm going to write that up in tabular format here. So first we're going to have our value a, which in this example is equal to 4. We're going to have a value x, which is an element of Cm. In this example, Cm is equal to C9. We're going to take the product of a and x, and we're going to take ax modulo 9, and that will be equal to b, which will be another element in the set Cm. So let's do some calculations here. First, we'll of course have 4 multiplied by 0. That'll give us 0. Just going to draw quick line here. 0 modulo 9 is 0. Then we're going to take 4 multiplied by 1. So of course 4. 4 modulo 9 is equal to 4. We're going to take 4 multiplied by 2, which is 8. 8 modulo 9 is 8. 4 multiplied by 3 is equal to 12. 12 modulo 9 is equal to 3. I'm going to take 4 multiplied by 4, which is equal to 16, of course. 16 modulo 9 is equal to 7. 4 multiplied by 5 is equal to 20. 20 modulo 9 is equal to 2. 4 multiplied by 6 is equal to 24. 24 modulo 9 is 6. 4 multiplied by 7 is equal to 28. 28 modulo 9 is equal to 1. And finally, we'll have 4 multiplied by 8, which is 32. 32 modulo 9 is equal to 5. Now, notice what we've done here. We've taken every element x in the set Cm. So you can see we took 0. Oh, I'm missing a 1 up here. Sorry. We took 0, 1, 2, 3, 4, 5, 6, 7, and 8. And we multiplied them each individually by 4, which was our a value. That gave us a product. We took that product, modulo 9, which gave us a new value, b, which is also an element of Cm. So you can see here we found 0, 4, 8, 3, 7, 2, 6, 1, and 5. Why is this important? Now that we've gone through that calculation, I'm going to read out a corollary that comes about from the theorem. And the corollary states, let A be an element of Cm. Then, if the greatest common divisor of A and M is equal to 1, then there exists one C in the set Cm such that A multiplied by C is equal to C multiplied by A is equal to 1 modulo M. Now, what specifically does that mean? What we did before in our calculation to show what the theorem 2.4.1 meant was that we took every value of the set C9 and multiplied that onto our A value, which was equal to 4. Then we took the product modulo 9 and out came a new value in which we called B, which is also a value of Cm. Only all the values of B are unique, and that means that only one element in Cm, when multiplied onto A, taken modulo M, equals 1. And in our instance, or in our example, that happened here at line 7. 4 multiplied by 7 is equal to 28. 28 modulo 9 is equal to 1. So just to write up that finally, what we have is A multiplied by C is equal to C multiplied by A, which is equal to 1 mod M. And for our example, that was 4 multiplied by 7 is equal to 7 multiplied by 4, which is equal to 1 modulo 9. The value that we multiply onto A is called the multiplicative inverse. And that is the value that when multiplied onto A, taken modulo M is equal to 1. The way we denote that is we write A to the power of negative 1 modulo M. This is the multiplicative inverse of A modulo M, which in our example here, as I said, is equal to 7. Now, I'm going to zoom out a bit here because I need some more space. Let's go with here. Why is that important at all? Recall that the context of this video is cryptology, and one of the primary purposes of cryptology is to enable confidential communication over the internet. The way we do that is that we take a message, mask it by doing some math, and then send it. The receiver then takes the now masked message and does some math to it that reverts the masked message back to its original content. We call the process of masking the message encryption. I'm going to write that here. The shorthand notation for that is, if we encrypt a message X, we write E parentheses X, where E of course stands for encryption. The opposite process is decryption. The way we write that is, if we have an encrypted message X, we write D parentheses E parentheses X, where D stands for decryption and EX is the encrypted message. To do this process of encryption and decryption, we need a mathematical scheme where we can transform one value to another and then back, while keeping the math and the method secret. And the multiplicative inverse can be used to set up such a scheme. To show you how the multiplicative inverse is used in a cryptographic scheme, I'm first going to go over some exponent rules. So I'm going to write that up here. Specifically, we're looking at the power of the power rule. And the power of the power rule states that if you have x to the power of a to the power of b, then that is the same as having x to the power of a multiplied by b in the exponent. Some of you might see where I'm going with this. What this means is if we have two distinct integers a and b, which produces the product 1, then we can take x to the power of a to the power of b, which then becomes x to the power of a multiplied by b, which is then just equal to x to the power of 1. Now you might say, D, there are no two distinct integers that multiplied together produces 1, and you'd be right under normal circumstances. But using our modulus arithmetic and the multiplicative inverse, there is. So why is that important? Imagine that we have two people who want to send a message to each other over the internet. We have Alice and Bob, A and B. Alice has a value a, and she's computed the multiplicative inverse of a and Bob has a message x. Alice has made the value a public, meaning that other people on the internet can see it. Bob is going to take that value and take x to the power of a, and that's how he encrypts his message x. So he'll take x to the power of a. He will then send that value, the encrypted value, to Alice, and Alice is going to decrypt it using the multiplicative inverse of a, which only she knows. What decryption then looks like is Alice will take the encrypted value, which is x to the power of a, and elevate it to the power of the multiplicative inverse. So Alice now has x to the power of a to the power of the multiplicative inverse, which is equal to x to the power of a multiplied by the multiplicative inverse. But when a and its multiplicative inverse are multiplied together, that's what we found out over here, they will produce 1. So Alice will have x to the power of 1, which is simply equal to x. In that way, Bob will have taken his message x, encrypted it, sent to Alice. She used her knowledge of the multiplicative inverse and the original value a to decrypt x by going through the steps here. And now she has the message received from Bob. What I've showed you here is the basis for the public key encryption scheme known as RSA that is in use all over the internet today. There's a couple of more steps to it, but this is the foundation for the scheme. A question arises now though, which is D. If the multiplicative inverse is to be used as an encryption scheme on the internet, surely the numbers that you choose must be much larger than 4 and 9 that you used in this example, because the numbers need to be hard to find such that the messages can be kept secret. And you'd be right about that. The next question then is, you found the multiplicative inverse by going through the numbers one by one. That's really slow. Surely there must be a faster method to find the multiplicative inverse of two numbers. And you'd also be right about that. And that method is Euclid's extended algorithm. And I'm going to go through that in my next video.